Welcome back, everyone. I am absolutely thrilled for today's explainer because we're tackling one of the most fascinating technological breakthroughs of our entire lifetime. I mean, if you've ever used ChatGPT, you've probably caught yourself sitting there wondering how on earth it actually manages to hold a conversation that feels so remarkably human. Well, today, we're pulling back the curtain. We are going to uncover the exact step-by-step pipeline that takes your raw text prompt and transforms it into that seemingly magical AI output. So get ready, because we are demystifying the transformer architecture. And this brings us to the ultimate question we really need to ask right off the bat. Does ChatGPT actually understand language, or is it just a really, really fancy search engine that's memorizing answers? Think about it. If you type in a prompt like, "The weather is nice today, I want to go to the beach," ChatGPT understands that intent in less than a second and generates a perfectly fluent, natural response. The secret behind this? It isn't magic. It's the transformer architecture. This was a groundbreaking model introduced back in 2017, and it completely changed the trajectory of artificial intelligence, literally giving birth to the large language models we rely on today. Okay, let's dive into this. Because to truly grasp how this works, we have to completely strip away our human illusion of language. You and I, we look at a screen and we see words, letters, sentences. We see, "The weather is nice today." The AI, it sees absolutely none of that. To an AI, the entire world consists exclusively of numbers. Before the model even begins to process anything, your sentence is chopped up into these little chunks called tokens, and each token is assigned a unique integer ID by something called a tokenizer. So the word today might become 14526, and weather becomes 8921. So, to make sense of all this, here's our roadmap for today. Number 1, converting text to numbers. Number 2, the core attention mechanism. Number 3, deep layers and multiple heads. Number 4, predicting the next token. And finally, number 5, the hardware and infrastructure needs. Let's start right at the beginning. Part 1, converting text to numbers. So we just learned that words are turned into ID numbers, but here's the fundamental problem. Just assigning an ID number to a word isn't nearly enough. The number 14526 doesn't inherently tell the computer anything about what today actually means, right? The model needs a robust way to understand if certain words have similar meanings or totally different contexts. Enter a process called embedding. This is where every single token ID is mapped into a massive, high-dimensional vector space. And we're not talking 2D or 3D here. We're talking anywhere from 768 to over 4,000 dimensions. And this brilliantly illustrates why embeddings are so incredibly powerful. Imagine a giant 3D graph, but expand that to thousands of axes. In this mathematical space, the spatial coordinates for the word doctor and the word nurse are physically plotted much, much closer together than the words doctor and banana. The AI doesn't actually know what a doctor or a banana is in the real world, but through these spatial coordinate vectors, it gains a deep mathematical understanding of semantic relationships. It just calculates which concepts belong together. Moving right along to part 2, the core attention mechanism. Now, before 2017, older AI models typically read sentences sequentially, just going word by word. The issue was, by the time they got to the end of a long paragraph, they essentially forgot what the very first sentence was even about. The information just degraded over time. The Transformer's monumental breakthrough was something called self-attention. Instead of reading sequentially, the Transformer looks at the entire sentence at the exact same time. So if you input something like, "I am studying AI at the company today," the model simultaneously considers every single token and essentially asks, which other words in this sentence should I pay the most attention to? To pull this off, self-attention uses 3 main roles: query, key, and value. I actually love thinking about this using a library metaphor. Imagine you walk into a massive library. The query is what you're looking for. It's your search keyword. The key is like the index or the title printed on the spine of every single book, telling you what that book offers. And the value is the actual useful content written inside the book. The model mathematically compares your query to every single key in the sentence to figure out exactly which values it needs to read and pull forward. Now, what's really interesting about this is what happens when those comparisons turn into actionable data. The model calculates the relevance between the query and the key, and then it runs that through a function called softmax to normalize all the weights into percentages. We call these attention scores. For instance, taking the token today, the model determines it has a 75% semantic link to AI, 20% to studying, and maybe only 5% to company. It then forms a brand new mathematical representation based on those exact weighted combinations. This is literally how the transformer grasps deep context. Which leads us to part 3, deep layers and multiple heads. You might be wondering, why rely on just one single set of attention? Well, the transformer doesn't. It uses multi-head attention. This means it's running multiple attention mechanisms in parallel, all at the exact same time. Think of it like having a whole team of specialized editors reading the exact same sentence. Head 1 might be entirely focused on the grammar. Head 2 is looking strictly at the semantics and the underlying meaning. Head 3 is tracking the timeline of events, and Head 4 is keeping tabs on the people involved. By combining all these specialized heads together, the model deeply understands incredibly rich, multifaceted linguistic features simultaneously. Let's move to how this builds into the broader architecture. Attention is amazing, absolutely, but it's not the final step. Inside a single transformer block, the data goes through this intense repeating cycle. First, attention calculates the context. Then, it passes through residual connections and layer normalization, which is basically just to keep the complex math stable. Finally, it hits a feed-forward network, which essentially enhances and reorganizes all that newly combined information. And here is the real kicker. This entire 4-step block, it repeats dozens, sometimes hundreds of times inside a large language model. As the data passes through these repeating layers, something truly incredible happens: abstraction. In the very first layer, the AI is really just understanding raw text. By layer 2, it's grasping distinct words. At layer 5, it forms sentences. By layer 10, it's holding on to complex context. And by the time you get down to layer 40 or beyond, the model is exhibiting what looks entirely like high-level logical reasoning. The deeper the layers go, the stronger the abstraction becomes. But as you can probably guess, doing this requires immense, mind-boggling amounts of computing power. Now for the big reveal. Part 4, predicting the next token. So the crucial point is, ChatGPT does not actually generate entire paragraphs at once. It doesn't sit there with a grand, predetermined plan for its whole essay. Behind all of this incredibly complex architecture we just talked about, it is doing one single thing: calculating the mathematical probability of the very next token. That's literally it. If the prompt is, "The weather is nice today, comma," the model calculates a 60% chance the next word should be I, 20% for so, and so on. It picks one token, outputs it, and then feeds that newly generated token back into the very beginning of the massive loop to guess the next one single token at a time. It's forming natural language through hyperfast, repetitive mathematical prediction. Which brings us to our final stop, Part 5, hardware and infrastructure needs. When you stop and consider the sheer scale of what we just discussed, running hundreds of attention heads, processing thousands of dimensions, and repeating it all across dozens of layers for billions of parameters, you realize the computational load is just astronomical. Every single layer is performing massive matrix multiplications. You absolutely cannot run this on a standard computer processor. The success of the transformer is inextricably tied to the evolution of GPUs, graphics processing units, because they are designed specifically for parallel computing. You literally need hundreds or even thousands of GPUs working in perfect sync just to train and run these models. And this shines a light on the unsung heroes of the AI revolution: AI infrastructure engineers. If the transformer model is the brain, the infrastructure is the nervous system keeping it alive. These engineers have to guarantee that thousands of GPUs have completely stable compute power. They build ultra-high-speed networks so data syncs instantly without bottlenecking. They use orchestration tools like Kubernetes to manage these massive models across giant server farms. Without this rock-solid physical foundation, all of that beautiful math simply falls apart. The infrastructure is just as absolutely crucial as the algorithm itself. Which leaves us with a truly fascinating reality to ponder. The transformer isn't magic. It doesn't possess a soul. It is an elegant, massive combination of high-dimensional math, matrix multiplication, and jaw-dropping infrastructure scale, all working together perfectly to predict one single token at a time. It's brilliant engineering. But if understanding language is really just crunching numbers and scaling GPUs, what exactly happens out there in the cloud the very millisecond you hit send on your browser? How does that specific API request physically travel through this immense server farm to deliver your answer? Well, you'll have to join us for our next explainer, where we'll track the complete physical life cycle of a prompt, from your keyboard to the GPU and back. Thanks so much for joining me today, and keep exploring.